So far, we've been studying systems differential equations in chapter 3, and we've been talking about some ways that we can approximate how solutions are going to behave without solving the system. So looking at the vector field, looking at null clines, and we did find some solutions in the phase plane. The next several lectures, these notes are going to deal with how we can actually find solutions for x and y separately for certain types of systems, in particular linear systems of differential equations. So let's just kind of start with the following example to motivate things, and then we'll add some complexities into these examples. But let's say, for example, I have two bacteria colonies. So I have one colony whose size is given by x, and I have a second bacteria colony whose size is given by y, and they're both functions of time. So here's our system. Dx dt is equal to 3x, and dy dt is equal to minus 2y. So before we find the solutions, we can make some observations from the differential equation and then check that our solutions mimic those observations. So one observation I can make, so part A is asking us to explain in practical terms how each of the populations is changing over time. So if we take a look at x and we take a look at the equation for y, I can see that actually this is not really a system. I have two separate differential equations. So this differential equation doesn't depend on y. This differential equation does not depend on x. So actually these two populations are not affecting each other at all. However big y is has no effect on the rate of change of x. However big x is has no effect on the rate of change of y. But if we look at each of these equations, I can see that, first of all, if we assume x and y are positive values, we're dealing with sizes of populations that are positive, then dx dt is going to be positive. So population of bacteria in colony 1 is always going to be growing at a rate proportional to the current amount of bacteria present. And for the colony 2, this colony's size is going to be decreasing as time goes on, and it's going to be decreasing in such a way that is proportional to the current size of the bacteria in colony 2. And so even without solving the system of differential equations, we've observed that the x dt is always going to be positive. So the size of colony x is going to go to infinity as time goes on. And we've observed that bacteria colony y is decreasing always. So as time goes to infinity, that population is going to head to 0. So even without solving, we can predict this behavior. But now let's solve these two differential equations, and we can say more about the solutions. So when things are changing at a rate that's proportional to the amount present, we've already seen these are exponential solutions. So I'm coming down to part B, dx dt is equal to 3x. That we could solve by separating, for example, but we could check pretty quickly that that solution is going to be some constant c1 times e to the 3t. And similarly, solving the system for y, dy dt is equal to minus 2y. And so for that one, if we separated and solved, we would get that y is some constant, maybe call it c2, times e to the minus 2t. So here we don't really have a system. We have two separate differential equations that we can solve separately. So next, let's take a look at what happens when we start to get interactions between these two equations.